Hello, welcome back to course on Advanced Quantum Mechanics. This is lecture 21. Remember that when we want to describe n particles, for n particles, we need to solve 6n equations of motion. And they are d by dt, x hat for the r's particle, the i's coordinate, equal to 1 over I h bar, commutator of x hat Ri of t with the Hamiltonian. And similarly, d by dt of p hat Ri of t equal to 1 over I h bar, commutator of p hat Ri of t, h hat of t. Now, we saw that it suffices instead to solve one, but solving just one equation of motion suffices actually. And what was it? Well, the equation of motion was that d by dt of u hat of t is equal to 1 over I h bar, u hat of t, h hat of t, with initial condition u hat of t naught equal to the identity operator. And why is that sufficient? This is sufficient because then we can calculate all of the time evolutions of all observables, because then f hat of t is equal to u hat dagger of t, f hat of t naught, u hat of t. This equation is important. We will later come back to it. All right, so we have reduced the problem of solving 6n operator-valued differential equations to the problem of solving just one differential equation for an operator-valued function, namely for this time evolution operator u hat of t. It does get even better though, because actually you can simplify the problem even further. Solving this equation of motion here for the time evolution operator requires us to find a matrix-valued function of time u hat of t. And a matrix has a lot of entries. A vector has fewer entries, at least in finite dimensions it would have. And this is what we can do. We can reduce the problem from having to solve one operator-valued function. For one operator-valued function of time, we can reduce it to the problem of having to find one vector-valued function of time. Actually, it suffices to solve for one vector-valued function of time. Strictly speaking, it's of course true that countable infinite is countable infinite, and a countable infinite by countable infinite matrix has as many matrix elements as a countable infinite component vector. But in finite dimensions, and often in quantum mechanics, for example, for quantum computing, we are looking at finite dimensional subspaces. There, it makes a big difference whether you have to solve for the n squared components of a matrix valued function of time or just for the n components of a vector valued function of time. So how do we do this? We start with an observation. And the observation is that only scalars, only Hilbert space scalars can be measurable. Only scalars. F bar of t equal to psi f hat of t psi can be measurable. Because basis independent. Everything that's basis dependent cannot be observable because we get to choose the basis and nature doesn't know what choices of basis we may want to do. So what matters is f bar of t, or are the predicted expectation values for all sorts of observables f. And how we calculate them is up to us. This is how we have calculated them. But there is a simpler way. So let us now rewrite this. We rewrite this in this way. We say that f bar of t is equal to psi, and then we use the fact that we had this equation, that we have this equation in the box here. F hat can be expressed in terms of f hat at the original time, and then applying the time evolution operator to the left and to the right. So we obtain that this is u hat dagger of t, f hat of t naught, u hat of t psi. Remember, f hat could be a position operator, a momentum operator, or some polynomial. So this is, of course, just f hat of t. But we can rewrite this slightly differently. You see, here, the implication is, if we bracket this way, the implication is that we take these three operators, u hat, f hat, and u hat dagger, and we multiply them together first, and then we apply them to psi on the right and psi on the left. But these calculations are associative because vectors and matrices multiply associatively. So therefore, we can choose the brackets differently. We can also write this as u hat dagger of t, f hat of t naught, u hat of t, psi, and then bracket this way, which simply means we first calculate the action of this operator on psi. If you insert resolutions of the identity here, then this is, of course, just a matter of column vectors, matrices, matrix, matrix, column, matrix, etc. So if we bracket in this way, then we first apply that operator on that vector. And then here, that's the same vector, just Hermitian conjugated. And here we take the operator in the middle, and the brackets tell us what operations we perform first. Now, when we do this, this suggests that we give this thing a name. And let us call it psi of t by definition. So define this. Let's spell it out. Define psi of t is u hat of t, time evolution operator acting on our state, psi of t. And this is called the Schrödinger state function. So this is the function of the Schrödinger state. It's no longer just the initial state, it's the Schrödinger state. And it is a function of time, so we call it a Schrödinger state function. Now, do we have any benefit so far from doing this? All we've done is really just bracketed differently. So instead of first multiplying those three matrices and then applying vectors left and right, we are first applying those matrices left and right to the vectors, and then at the end we apply that on the f hat. That's all we've done. It doesn't look like we have simplified anything. And in particular, it seems that we still have to calculate u hat of t. You see, we now have that f bar of t is equal to psi of t, f hat of t naught, psi of t. But don't we still need to calculate u hat of t? But don't we still have to calculate u hat of t so that we obtain psi of t equal to u hat of t psi? Then, if that were the case, then we would not have gained anything. I mean, certainly we can do it this way. We can calculate the time evolution operator, then use it on psi to obtain psi of t, and then we can calculate all observables this way, but no benefit because we would have to calculate the time evolution operator. But our aim has been to simplify things, that we don't have to solve for the time evolution operator, but instead just solve a vector valued equation. And amazingly, this is possible. Actually, no. It is possible to calculate psi of t without calculating u hat of t. And if we can calculate psi of t, remember, then we're done, because once we have psi of t, well, then we can calculate the time evolution of any prediction we want. We just take the operator at the beginning time, and we never need to calculate the time evolution of the operator. It's always at the initial time. And then knowing psi of t, we can calculate our predictions later on. But how does this work? How can we calculate psi of t without having first calculated u hat of t? Well, let's do the calculation. How? Well, let us start with the defining equation for the time evolution operator. So we have IH bar d by dt u hat of t equal to u hat of t h hat of t. This was the defining equation for the time evolution operator. Now we can multiply here u hat dagger of t, u hat of t, because u hat of t, because this is just the identity. This is the identity. Why? Well, because u hat of t is unitary. And remember, unitary means u hat dagger of t is equal to u hat inverse of t. All right, so we didn't do any damage to our equation. It's still true by just multiplying with the identity and writing the identity in a slightly complicated way. The point of this is that we're going to get in a better place from here if we now apply that equation on our state psi. So let's apply the equation left and right on our state psi. D by dt u hat of t psi equal to u hat of t h hat of t u hat dagger of t u hat of t psi. Now I hope you see why it was beneficial to multiply these two operators here. That's because now we have a u hat of t on the right. That u hat of t is acting on psi. Same here, u hat of t acting on psi. And that's the thing that we gave a new name here. This thing we called psi of t, right? So this is psi of t. So therefore, we now arrive at this equation here. We arrive at the equation that IH bar d by dt psi of t obeys, I mean the psi of t obeys a certain differential equation, namely this one. Now, that looks good because it is a differential equation for the vector valued function psi of t. But it still requires u hat of t, the time evolution operator. But we want to get rid of it. We don't want to have to use it, to know it, to calculate it. We don't want that. So what we do is we give this thing a new name. We call this h hat s of t. And it is called, this is called the Schrödinger Hamiltonian. Well, then we obtain that IH bar d by dt psi of t equal to Schrödinger Hamiltonian acting on psi of t. And there's one bar too much in there. All right, so we have this. Now at this point, we draw a box around this because it's a super important equation. This is of course the Schrödinger equation. So this is the Schrödinger equation. And it appears we are done at this point, because we have arrived at the differential equation for psi of t, and if we can only solve it, then we seem to be done, because then once we have psi of t, we can go back to here and calculate any prediction for any observable we want. We just plug the psi of t in here for any observable whose time evolution we never have to calculate because it's taken at the initial time. And we can make all predictions, right? So if only we can solve the Schrödinger equation, if only we can solve this differential equation for a time-dependent vector-valued function, then we are done. But of course, you notice that something's fishy here, because we used to have u hat of t in here, and then we said this is disturbing because we don't want to be bothered having to calculate u hat of t. So we just absorbed it in the definition of this so-called Schrödinger Hamiltonian. What's the deal with that? We somehow swept it under the rug here. In other words, how do we know what the Schrödinger Hamiltonian is without first calculating what the time evolution operator is? Remember that when we start with the classical theory, then going through the Poisson bracket formalism, we arrive at the Hamiltonian H hat. This funny Schrödinger Hamiltonian is not the same thing. What is it? Can we tell what the Schrödinger Hamiltonian is without having to calculate the time evolution operator? In fact, we can. Notice. We can obtain H hat S of t from H hat of t without calculating u hat of t. Well, how come we are so lucky? Let's see how that works. How? Well, first, we know the relationship between the Schrödinger Hamiltonian and the original Hamiltonian. We know that the Schrödinger Hamiltonian is given by u hat of t, h hat of t, u hat dagger of t. This is what we have to work with. Now, let us remember that we assume that h hat of t is a polynomial. In x hat of t and the p hat of t. Of course, there could be many position operators, many momentum operators, but there's no point in keeping those indices around. So we write it as h hat of x hat of t of p hat of t, and the coefficients could also be time dependent. Let's do it for an example first. For example, we could take the Hamiltonian of the form h hat of t, or let's just spell it all out. H hat of t, h hat of x hat of t, and p hat of t and t could be p hat of t squared divided by 2m plus alpha of t, which is some number valued function, alpha of t times x hat of t. just to pick some random example. See, this has the x hat, x hat of t, p hat of t, and it also has some explicit time dependence in it. So what then is the Schrödinger Hamiltonian? Let's see. Then what is h hat s of t? Well, remember we have h hat s of t. The Schrödinger Hamiltonian is u hat of t, and then h hat of x hat of t, p hat of t, t and u hat dagger of t. And in our example, up here, what is that then? Well, so in the example, this is then u hat of t, and then let me spell out a little bit more carefully what we are dealing with. 1 over 2m, and then it's the p hat of t, p hat of t, plus alpha of t, x hat of t, and that multiplied with u hat dagger of t. This is the Schrödinger Hamiltonian. We still seem to be dragging around those pesky time evolution operators that we don't want to be bothered calculating. But let's see what happens next. In here, we can squeeze in an identity operator, namely u hat dagger of t times u hat of t, which is the identity, right? Let's squeeze that in here. So this is then u hat of t, and then it is 1 over 2m, and then p hat of t, u hat dagger of t, u hat of t, and another p hat of t, and actually, let's just write it like this, and then we have a u hat dagger of t plus alpha of t, and then u hat of t, x hat of t, u hat dagger of t. It doesn't look like we've improved things because now we have even more time evolution operators in there when our aim was to get rid of them. The trick is that now all the occurrences of the time evolution operator are such that it's sandwiching one of the observables. You see, here we have u hat, p hat, u hat dagger. This repeats. Here we have u hat, p hat, u hat dagger. And here we have u hat, x hat, u hat dagger. It's always a u hat to the left, that's the observable, and then u hat dagger to the right. Now, let us remember what that combination is. Remember, we have this equation here. See that? This equation. Let me try to copy it. All right. Copy. And now we move that down here. So recall, and then we put that here. Okay, so here we have our equation, and from it, we also obtain that if we now multiply this equation from the left with u hat, then we have u hat of t, f hat of t, and from the right with u hat dagger, then we have u hat dagger of t equal to f hat of t naught. Okay, so what we did here is that we multiplied this equation here in the box from left and right with operators, from the left with u hat and from the right with u hat dagger. So we obtained this equation, but you see this is now of that sandwich form that we are encountering up here. This is a u hat observable u hat dagger. That's what we have here, u hat observable u hat dagger. And what is it? It's the observable at the initial time. And the same appears up here, u hat observable u hat dagger, u hat observable u hat dagger. So what we obtain is that the Schrödinger Hamiltonian is equal to, so therefore we obtain that the Schrödinger Hamiltonian is equal to 1 over 2m, and then this expression here collapses into just p hat of t naught times p hat of t naught plus alpha of t x hat of t naught. And now we did get rid of the time evolution operators. So therefore, in general, that is to say, i.e., for all Hamiltonians, x hat of t, p hat of t and t, we have that the Schrödinger Hamiltonian is equal to the Hamiltonian that we started with, but with the observables frozen at the initial time. How do we see that? Well, we did it for this example, where the Schrödinger Hamiltonian turned out to be the original Hamiltonian, p squared divided by 2m plus alpha of t x hat, except that in the original Hamiltonian, these guys would have been time dependent. Now, they are not. The operators are frozen in time. And we showed this using the trick that whenever we had when we had the product of two observables, we inserted the resolution of the identity in a sense by writing the identity operator as u hat dagger u hat. And if there had been the fifth power of p hat, we could have pulled the same trick, just inserting more resolutions of the identity. And in the same way, it works for all polynomial Hamiltonians. Therefore, we have this statement here. So the Schrödinger Hamiltonian is the same as the original Hamiltonian, except that the operators are frozen in time. This is no big deal if there is no time evolution here, because the Hamiltonian is in any case time independent unless if you put a time dependence in there. But this is the case that we are interested in here, the generic case where there might be an explicit time dependence too. And that's where it makes a difference. So the Schrödinger Hamiltonian is the original Hamiltonian with the operators frozen in time. So let's summarize where we arrived. Summary. We can calculate all predictions and by predictions we mean f bar of t this way. Solve the Schrödinger equation, IH bar d by dt psi of t equal to Schrödinger Hamiltonian of t, psi of t, with initial condition that psi of t naught has to be the initial state vector, obviously, and with the Schrödinger Hamiltonian being equal to h hat of x hat of t naught, p naught of t naught and t. And if there are more operators around, because we have more particles, many dimensions of space, then there would be more operators, but it works exactly the same way. So we calculate our predictions this way. First, we solve the Schrödinger equation with this initial condition, with this Hamiltonian, and then we obtain our prediction for an observable f as a function of time as psi of t, Schrödinger state vector function, f hat at x hat of t naught and p hat of t naught, and psi of t, right? Because this is f hat of t naught. F hat of t naught, f hat is some polynomial in the x and the p. If f hat is simply x hat, well then it's x hat of t naught. If it's p hat of t naught, and if it's a polynomial of the x and the p, then it's the entire polynomial, but every operator is frozen in time. Now, definition. We call this method for calculating f bar of t the Schrödinger picture. States evolve, states psi of t evolve, and observables f hat of t naught are frozen. Definition, the previous method the method that we used all throughout this course so far, is called the Heisenberg picture. What we did today, the showing of the equivalence of the Heisenberg picture and the Schrödinger picture was first done by Dirac. Heisenberg came up with quantum mechanics first, then about half a year or so later Schrödinger, and then another half a year or so later Dirac showed that the two pictures, the two methods are really the same, equivalent. So here, just to remind you of how this works again, here we have that IH bar d by dt f hat of t is equal to a commutator of f hat of t with h hat of t. The observables evolve the state psi is frozen. All right. Any other comment? In the Heisenberg picture, we can calculate, if we want to, the time evolution operator this way. Namely, that d by dt of u hat of t, no, ih bar d by dt u hat of t is u hat of t, h hat of t, and u hat of t naught is the identity operator, right? That's how we did it. Now, in the Schrödinger picture, we don't have h hat available. How do we calculate it then? In the Schrödinger picture, well, let's see. We have the following relationship between the Heisenberg Hamiltonian and the Schrödinger Hamiltonian. The Heisenberg Hamiltonian is u hat h u hat dagger. So from this we have, let's just copy it and paste it. So copy. Yeah. Okay. So we have this, and therefore we have that the Heisenberg picture Hamiltonian is equal to u hat dagger of t, Schrödinger picture Hamiltonian, and then u hat of t, right? Just by taking this equation, multiplying it from the left and right with u hat dagger and u hat. But this means that we can now replace this this Heisenberg picture Hamiltonian by that expression here. So what we obtain is, therefore, and I'm just carrying forward this equation, except I replace the Hamiltonian. So you now have ih bar d by dt of u hat of t equal to u hat of t, and then what? Well, then the h hat, the Heisenberg picture Hamiltonian, is this expression. Let's write it out. It's u hat dagger of t, Heisenberg Hamiltonian, u hat of t. And since u is unitary, this means that ih bar d by dt u hat of t equal to Schrödinger picture Hamiltonian u hat of t. So if we want to calculate the time evolution operator in the Schrödinger picture, this is how to do it. Okay, so now we know how to calculate the time evolution operator in the Schrödinger picture and in the Heisenberg picture. And we also know how to calculate predictions for observables f bar, either in the Heisenberg picture or in the Schrödinger picture. Now we are, of course, very familiar with all sorts of calculations in the Heisenberg picture. Let's see how this looks like in the Schrödinger picture. So let's look at the Schrödinger equation. Schrödinger equation in a basis. So initially, the Schrödinger equation looks like this. Without choosing a basis, it looks like this, right? We had it up there. Psi of t. Now, choose, e.g., a discrete basis. Choose, for example, a discrete basis of vectors Bn. Then, if we multiply the Bn vectors from the left, then we have IH bar and d by dt, and then Bn psi of t. We are allowed to pull the d by dt in front because the Bn is constant. It's just a fixed choice of basis, not time dependent, equal to, and then we have here a Bn Schrödinger Hamiltonian. And then in principle, I could write here the psi of t. But let's insert a resolution of the identity. Sum over m. And then Bm psi of t. And what is this now? Well, this is obviously the wave function of psi in the Bn basis. So what we have is that IH bar d by dt of psi n of t, this is psi n, this is psi n of t, is equal to, and here we have the matrix elements of the Hamiltonian, which is literally a matrix, right? Sum over m, and then it is the matrix of the Schrödinger Hamiltonian, and it's an m matrix elements, and here we have psi m of t, because that's again this matrix element here, this overlap here. Right, so this is the Schrödinger equation in a basis. This is the Schrödinger equation in a basis. And what is this Hamiltonian as a matrix explicitly? Well, the Hamiltonian is some polynomial in the x hat and the b hat. And remember, we found matrix representations for x hat and b hat. We found how they look like as matrices when we choose a discrete basis, such as the Bn basis. So we can just plug that in there, and then we get the matrix for the Hamiltonian. And then we can solve the Schrödinger equation here, and it's an equation where this is known, and the operators also don't evolve in time in there, except for the possible time dependence of the prefactors in the polynomial, the coefficients in the polynomial. The actual operators are in the Schrödinger picture frozen in time, remember. And what we need to solve for is these column vectors here, these columns of coefficients here, psi n of t. Now, how does the Schrödinger equation look like in a continuous basis? Schrödinger equation in a continuous such as the basis of the position eigenvectors. Well, we start again with the abstract Schrödinger equation, d by dt psi of t equal to Schrödinger Hamiltonian acting on psi of t. And then we apply x from the left. So we obtain IH bar d by dt of x psi of t. And this is then x h hat s of t. And here we could just write psi of t again, but let's again insert a resolution of the identity. Psi of t integral, and this doesn't want to go there. Okay, I think I know how to do this. Okay, so now that should work. Yep. Okay, now I can put a dx there. All right, dx prime. All right, so what do we have? This is clearly the wave function of the state psi, the position wave function. So this is d by dt. And then here we have psi of x, which now also depends on time because we are working in the Schrödinger picture. So this is equal to that. And this is equal to integral. And then we have the matrix elements, so to speak, of the Hamiltonian in the position representation. So this is the Hamiltonian in the Schrödinger picture of t, and it depends on x and x prime, where just as before, these are indices, but continuous labels, continuous indices, if you still want to view it as a matrix. Times, well, this is psi of x prime and t dx prime. Now, how to make sense of this? Here, this is an operator. This is the set of matrix elements of our Schrödinger Hamiltonian. And just like we previously had a matrix acting on a column of coefficients, now we have the same thing, but with a continuous label here. Now remember that we faced this kind of structure before. We said that the position operator in the position representation acts through an integral. Every operator acts through an integral this way because ultimately it's represented through its matrix elements, and then you have to do this integral. And the same was true for the momentum operator. Remember, it was having matrix elements of the form derivative of the Dirac delta. And then we had to integrate it over. And then we decided that this is a little tedious, and the outcome would be predictable. We know what happens when you apply a momentum operator in the position representation. If you take its matrix elements, namely the derivative of a Dirac delta, and then you integrate it over some wave function, then you end up differentiating that wave function. That's why we introduced the shorthand notation for quickly writing down what happens when you have a position or momentum operator acting on a wave function. And in fact, how a polynomial in the position momentum operators acts on wave functions. So now, let me cut this short and go right to the shorthand notation. So using our shorthand notation, we obtain that x hat dot acting on psi of x and t is equal to x psi of x and t. P hat dot acting on psi of x and t equal to minus I h bar d by dx of psi of x and t. We just draw from what we proved earlier in the course. And therefore, the Schrödinger equation in the position representation becomes IH bar d by dt psi of x and t equal to Schrödinger Hamiltonian expressed as a polynomial in the x hat dot, the p hat dot, and a possible time dependence in the coefficients acting on psi of x and t. All right, this now is the Schrödinger equation in the position representation as you've seen it many times before. Schrödinger equation in position representation, or position basis, let's say, and the position basis, eigenbasis. Now, let me say something to summarize our course so far. When you compare with textbooks, conventional first textbooks on quantum mechanics, such as Griffith's, you will find that often the Schrödinger equation just falls from the sky on page 1. I think in Griffith's book, the one with the cat on the cover, the Schrödinger equation literally falls from the sky on the first page. You're just presented with the Schrödinger equation and basically you proceed to solve it for the rest of the course. And why is that? I think it's just a tremendous shortcut. You're just presented with the Schrödinger equation without much explanation, and then you're supposed to solve it. Fine, you can quickly go and solve for the hydrogen atom and so on. But of course, it's then unclear where it comes from. Where does the Schrödinger equation come from? And that's one of the main goals I had in this course, namely to clarify that. What is really the structure of quantum mechanics? How is it related to classical mechanics? And now you see why it is so difficult to explain the Schrödinger equation in a few sentences or even just in a few pages. Because if you remember what it took to get to this point, the Schrödinger equation in the position representation is quite a few steps. We started from the Newton equations, classical mechanics in the Newton equation form. And then we said, they can't be quantized. We need to upgrade that. So we went to the Hamilton principle, formulated everything in terms of the Hamiltonian using Poisson brackets. At this point, we identified that classical mechanics is described by a Poisson algebra. And we followed Dirac to find out that this Poisson structure is rigid. You cannot do much without messing with it in a brutal way, which gravity might do. But if we keep gravity out of the picture, there's very little you can do. And you end up with quantum mechanics. Same Poisson algebra. In terms of the Lie bracket, same Poisson algebra, but in terms of the multiplication, slight non-commutativity. And in this way, we arrived at the Heisenberg picture. The observables were evolving in time, just like in classical mechanics, where the x evolves in time, the p evolves in time. The initial conditions don't evolve in time. It's just the x and the p. And so in the Heisenberg picture, same thing. That's the natural formulation of quantum mechanics that we obtained when we start with classical mechanics. And then we had to study the representation theory of the Heisenberg picture. And we found that it's completely different from in classical mechanics, because now we have to work with complex Hilbert spaces. So we studied the representation theory there. And we found that there are many different bases you can choose: the position eigenbasis, momentum eigenbasis, the eigenbasis of any observable. that's self-adjoint, you can use. You can use any Hilbert basis, in fact. And then we said, now we can change the way we evolve the mathematical quantities here. So we had to switch from the Heisenberg picture to the Schrödinger picture, where suddenly the observables are frozen in time, but the initial state vector picks up time dependence. And once we had that, then we were able to write down the Schrödinger equation in the position representation and arrived at the Schrödinger equation in the way that Schrödinger first came up with it. So the Schrödinger equation is a special choice in that it is a particular choice for what evolves mathematically, namely the states rather than the operators. It's also a choice in that a particular basis is chosen, namely the position representation. And also there is a choice in that we do not do what in principle ought to be done and work with the tedious formulation of the Schrödinger Hamiltonian as an integral kernel that depends on x and x prime, and then we integrate it over. But instead, we use the shorthand notation that shortcuts to the result of what this integral kernel does on these wave functions. And then once you've made all of those choices, then you arrive at the Schrödinger equation. But I hope that by now, you should be able to move very freely through all possible representations, time evolution pictures, Schrödinger picture or Heisenberg picture, and you see the Schrödinger equation for what it is, a special case of a special case. And what's really going on in the background is that the time evolution operator is governing the way that the dynamics unfolds. And that time evolution operator can be chosen to act either on the states, that is to say on the vectors, that's Schrödinger's choice. It can also be chosen to act instead on the operators, that's the Heisenberg choice. And there are other choices as well. Dirac came up with another way of doing the time evolution, and we will cover that as well. But this is as far as we got today. See you on Wednesday. Bye-bye.